All right, welcome back. I'm going to cover section 1.2, Science and Context. And this was actually a really tough chapter or section for me to put into notes because it's all over the place. Literally, it's all over the place because science does not occur linearly. It just flows, basically. So I'm going to talk about how attitudes and experiences can generate new ideas, explain why peer review is important, what's the relationship between science and society, and then list some common practices that you can find in both science and engineering and how those two can go hand in hand. So science is not, it's not linear. It occurs dynamically and involves some of the questions or steps that we talked about already with scientific inquiry. We ask questions, we make observations, we seek evidence, we share ideas, we analyze data. Notice that these parts do not proceed linearly. Real science involves many activities that tend to loop back on themselves. You build up on knowledge as they proceed. And like I said, it's really hard to just like cut a direct path as to what you should do step by step because you're basing your next step on the information that you gathered at that step and so on. So this is probably the gist of section 2, this diagram right here, where here we have our steps for scientific inquiry. You make observations, you ask questions, you share ideas, you find inspiration, you explore the literature, but you have to realize there's outside forces acting upon that exploration and discovery, like serendipity. Sometimes you just get lucky. Personal motivation, a surprising observation that you notice, a practical problem that you want to solve, or new technology is developed and you apply that new technology into a different study. Curiosity. But then this circle can interact with this green circle where you test your hypotheses, right? Using an experiment and you record actual observations and then you try to interpret that data and say, what does it mean? And then once you have that data, then you can pass it on to the community for analysis and feedback where your peers or other scientists review it and they try to replicate it to see if they get the same results. And if that's the case, maybe you get published or you have discussion with colleagues and you can come up with new questions and theory building, which can then move on to this sphere, the benefits and outcomes of your investigation. You know, what kind of technology can be developed? What kind of knowledge can you build upon? Does it satisfy your curiosity? How does it address societal issues? Does it solve some of them? Does it change policies? Do you solve everyday problems based on what you did? And so you can see lots of different arrows and how they interact with each other. Okay, so you need to understand the role of science and how it plays in our society and the limitations that it can have. So the thing is about science, whenever science doesn't really have emotions. Okay, you're supposed to be like non-emotional. So there's really no ethical or moral viewpoints, but we do see ethics involved in science as well as moral viewpoints. And so we want to be very careful when we conduct investigations and stay away from being biased, which means your personal rather than your scientific views. So in this cartoon diagram here, we have this man who's kicking this petri dish in the trash because you can see that its coloration does not meet all the other results, and he doesn't want that data to show up in his report. He wants to be, he wants to support his hypothesis that he started with, and he's actually kind of like guiding the results. And that's not what we want in science. We don't want to favor a result. We want to try to remain neutral and conduct it and see what the end result is. This man over here is named Peter Glick, and he was one of the leading scientists in climatic changes, primarily with water. And I remember him because when I was in college, I was actually like this ambassador. Let me just start all over. Gustavus holds a 2-day conference every year called the Nobel Conference, where they pick a theme and they invite the top researchers and field experts to campus for a 2-day kind of, they share their information. There's lots of discussions going on. And then not only that, these scientists, they also meet together and they hear from each other. And we try, theoretically to come up with solutions or a pathway of how we can handle it. And so this was the year where I think it was like looking at water or climatic changes in water. And Peter Glick, like I said, leading scientist in his field, came and he presented and he was phenomenal, just a phenomenal presenter. Now I was his ambassador, basically his chauffeur. I took him from one place to the other. I had an agenda or his itinerary, and I led him from campus to campus. I guided him. I had to sit down and eat lunch with him. And this guy was like a statue. I could not crack this guy. I'd ask him questions to try to engage in conversations, and it was always yes or no. And I was like, oh my gosh, this is like a nightmare, like literally a nightmare. Like everyone else is interacting with their lead, expert, and here I am. I can't even get two sentences out of this guy, right? So it's dinner or supper on the first day. And I'm like, I don't know if I can do another day of this. Like I'm literally thinking of like tag teaming out with my friend Julia. And finally, I just mentioned at the dinner table, so are you a Trekkie? And he's like, yes. And I go, have you seen the new Star Trek? Which was the remake with Chris Pine. And he's like, yes. And then all of a sudden, like barriers were broken down. Like this guy's a huge Trekkie fan. And I was like, oh my God, I'm like grasping at straws because I, have not seen Next Generation at that time or Voyager or any of, the TV shows, but I did see Star Trek, and I, just kind of played along and did my best. But after that, it was way more fun to bring this guy around campus and to talk to him because like he actually engaged in conversations. But a couple years after that, he got into trouble because he actually lied about a few things. And he states here that my judgment was blinded by my frustration with the ongoing efforts, often anonymous, well-funded, and coordinated, to attack climate science and scientists and prevent this debate, and by the lack of transparency of the organizations involved. So basically, he lied about some of his research. And, policies are based on research. And so he lost credit. He's no longer considered top field. But not only that, the trust between society and science was hurt, was severed a little bit. So there's this article out there, I think it was by the New York Times, says Glick's admission is sure to further intensify an already bitter debate between those who accept the scientific consensus on climate change and those who doubt it, and further deepen the uncertainty of many Americans about which side is right. This is going to stick. For those people who don't believe climate change is real or think that it's part of some UN conspiracy to control their lives, this will reinforce that view. Those who don't believe that, who think there is a massive conspiracy by corporate and conservative interests to muddy the science on that side, view Peter Glick as a hero. So he lied, but those that want to save planet Earth said, yeah, we're, good thing you did, because now we got some like really, policies to help planet Earth. And then those that are on the other side of the fence are just like, we can't trust science. You just can't. Okay, so he added somewhere in the middle, it could confuse people and confuse the climate debate for some time to come. And it does. There are some naysayers out there. There are some people that are like super pro, like, oh my gosh, Earth is, we're ruining it, blah, blah, so on and so forth. So whenever you read anything about research, look at who did the research. Are they actually experts in their field? Where does it come from? Are they, do they work for an oil corporation? Do they work for Greenpeace? Whatever. So just realize that some people can be biased in their research. Okay, the final thing I want to cover is how the scientific inquiry process overlaps with the engineering process and how they are similar. So these are the 4 similarities. Number 1, they both develop and use models. So there's different types of models out there. They could be mathematical models or computer simulations to try to predict the outcome of something. They both use math. They're going to look at relationships between variables to analyze and interpret that data. So a lot of times math is used. Statistical analysis is, for example, analysis. They both construct explanations and design solutions to problems. So they're going to look at how those variables relate to one another and how it's supported by the evidence that they have to construct what's going on here. And then finally, they're going to engage in argument from evidence and try to persuade the others that their explanation is correct. So here's the scientific inquiry that we've kind of gone through. Like you ask a question, you carry out investigations, you identify your independent, dependent variable, you analyze and interpret that data, you might use a model, so on and so forth. Here's a diagram showing the engineering model where you have an idea, a concept, you plan it out, you design it, you develop it, maybe use a tiny little model, then you build a bigger model, and then you launch it and try to get results. Here's a scientific model in red down at the bottom. So a lot of times they do overlap in the concepts, but I have stated 2 slides previously. These are the 4 that they do have in similar, or that they have in similarity. Okay, so that does it for section 1.2. I talked a little bit about attitudes and experiences that can help generate new ideas. Peer review is super important, so that way we can replicate results. The relationship between science and society, how science can be used to solve societal problems, and then to list practices that are common in both science and engineering.